This is the vertical circle assessment. In this situation, we have a car traveling around a circle. The radius of the circle is 5 meters. The mass of the driver is 60 kilograms, and he feels 3 times heavier than he does normally. Okay. First thing we want to do is draw a force diagram for the bottom here and the top here. So at the bottom, our forces are going to be mg, force of the earth, pulling down on the driver, with a force that's going to be equal to the mass times the gravitational field strength of the earth, which will be 600 newtons. And we got a normal force. Our normal force, when the driver says he feels 3 times heavier, what he means is that he feels the normal force 3 times as much as he really should. So our normal force is going to be equal to this, our mg times 3. So we know the normal force should be 1800 newtons. Alright, at the top, we're going to have a different force diagram. We have the normal force pushing the car down and the earth pulling the car down. So we have two forces, mg, which is still 600, and the normal force, but we don't know how much it is. So I'll just draw it in at that length. First question we got to answer is at what speed is the driver traveling? So in order to do this, we got to have a few assumptions. We know that at the bottom, our net force will be the normal force, this guy. So at bottom, F net will equal N minus mg. We also know that since he's in circular motion, our net force is the centripetal force, which is mv squared over r. We know that net force is both these things, so we can set it equal to each other. N minus mg equals mv squared over r. So that's great. We know that N, we can figure this out pretty easily. That, well, let me just write this out. N, since he feels 3 times heavier, N is going to be 3 mg. And since mg is 600, N equals 3 times 600, N equals 1800. So 1800 minus 600 is 1200. So that's half of the equation. We know his mass is 60 kilograms. We don't know his velocity squared, so that's going to be left out. And we know r is the 5 meters of the sphere. So we're going to work this out. Yeah, we can work this out. 5 times 1200, let me plug this in. 5 times 1200 is 6,000 equals 60v squared. So 6,000 divided by 60 is 100 equals v squared, and the square root of 100, the square root of r, of v squared, is going to be 10. So 10 is equal to v. So our velocity is 10 meters per second. But sweet. That's the first question. The second question is, how does the driver feel at the top of the sphere? So to do this, we can use our same underpinnings we used before. But this time, because he's at the top of the sphere, our F net is going to be N plus mg. And thus, this guy will be n plus mg equals mv squared over r. And this assumption goes away because he's not at the bottom anymore. So let me erase the work. How does he feel at the top of the sphere? We got f net equals n plus mg. F net also equals mv squared over r because he's still in circular motion, so n plus mg equals mv squared over r. Sweet. Now, in order to figure out how he's feeling, what that's really talking about is how much normal force does he feel? What fraction of his normal force is like, how does his normal force compare to his mg, which is his actual weight? So we're going to solve this for n. So n is going to be mv squared over r minus mg. And then we can just plug in our numbers and solve. Let me use a different color. N equals m 60, v squared is 10 squared, over r, which is 5, minus mg, which is 600. So this gives us n is equal to 6,000 over 5 minus 600. N is equal to 1,200 minus 600. N is equal to 600 newtons. So, since his mg is 600 and his n is 600, his normal force is 600, he feels the same as he would any other time. And so the driver feels a normal weight because mg equals n. So he feels normal. Let me write that. He feels normal. Next thing we want to do is, they ask us, at the minimum speed the driver could go and just stay on the sphere, how does he feel? And so we know at the minimum speed that he can go around this thing, our n is just barely going to be 0, our normal force, because he's still touching, but he's not touching hard enough for the surface to actually push back on him. So we're going to say that at the minimum speed, at the minimum velocity, n equals 0. And we were just talking about before how your perception of weight is based on your normal force. So if normal force is 0, he feels no weight at all. The driver feels weightless. And boom. That's our answer for the vertical circle assessment.